main goal for today. Main goals, say. The first one is that we're going to prove that, gamma, the map, the graph of the gradient of U is invariant under the Hamiltonian flow. And here we only assume that U is C1, so that is a big, improvement from C2 to C1. The second point is that we're going to discuss, because you're going to see at first the proof today is a little bit ad hoc, we ad hoc in the sense that we see what we need to prove, right? So, so the key point I want to discuss today is that why do we get such a proof? I mean, we can trace backward and try to think deeper. I mean, why did we come up with such a proof? And this amounts about the relations between Euler-Lagrange equations, and again with the Hamiltonian ODEs always, And then I want to discuss the third point. I want to discuss is about ODEs, right? It's ODE theory. What are we talking about here? There are some hidden subtleties that I want to discuss, and eventually, the last point is rather quick because we're not yet going to go too deep into that. It's about the point that what if our solution U is not C1, right? Again, this is the last point. Is going to be rather vague and brief for now. We focus on them later. Okay. We stated the theorem in last two lectures as well. I mean, in both of the last two lectures, but let me recall it. You have C is the energy level. I'm looking at the lab panel now, and we assume that U in C1 of the torus solves the equations, Hamilton-Jacob equation, H of x du equal to C in the torus. And again, the claim is that the graph gamma is invariant under the Hamiltonian flow. And let me recall quickly what we did last time, because we see that there's a duality between Lagrangian and Hamiltonian frameworks. So it's always good to go from one to the other and vice versa. So today we're going to use the Lagrangian framework. And we also need to discuss why, right? So that's for later. Sometimes you see that, why it's better to use the Hamiltonian framework and why it's better to use the Lagrangian framework. So, so I should have said that, so you have that, invariance under the Hamiltonian flow. Can be proved to be equivalent under like invariance under the Lagrangian flows as well. So it's useful to go between the two, right? So earlier, if we have USC2, then we used the Hamiltonian framework. I'm not gonna recall the whole proof, but I'm just saying that we have H of x du equal to C, then we can differentiate in x, okay? And when you differentiate in x, I believe that we get the gradient in x plus the gradient in p times d squared of u equal to 0. And that allows you to see that dxu occurs, right? So that was the early idea that, if it's C2, we use the Hamiltonian framework. So for today, then we only have U is C1, and then, it's not possible to use directly the Hamiltonian framework because we really don't know how to compute dx of h, right? Because to compute dh of h of the Hamiltonian, that means that we have to differentiate the equation in h. And that is simply not possible because I don't have that U is C2. Um, so again, it's a technical issue, but then the real question is that why it's better than to use the Lagrangian framework. So we cannot differentiate the PDE. So again, it's an ad hoc point because we knew it already, but again, I want to explain eventually why. So it's better to then use the Lagrangian framework. Okay. So that's what I want to discuss with you. And again, the proof is not too hard. There are some hidden points there, but I mean, the proof is, you see it, right? I mean, you can say, okay, you can finish the proof in 10 minutes. But then again, we're gonna see that there's certain points that are hidden there. Anyhow, before doing that, I want to mention this point first, that invariance in Hamiltonian is same as invariance under the Lagrangian. We discussed that already in the last part of the previous lecture, but I want to recall it because this is a very important point. And it's better that we get fluent and get used to this point because it's really useful for later uses in various different aspects. And it might be also useful for your research because it's going between different frameworks and having the equivalent points allow us to be more flexible. Okay, so let me recall this one quickly. Let's have a look at the left panel now. Okay, I have the curly L here as the map, mapping from the XP to XP. Okay, so again, we kept recalling it, but I mean curly L is mapping from XV to XP. And here you have P is dVL of XV, and curly L tilde is nothing but L inverse. Curly L inverse is mapping from XP to XV, where V is dPH of XP. Okay, so it's sort of same on and same on. Again, so one just needs to get used to it. So you have L and L tilde as CK diffeomorphism from Tn cross Rn to Tn cross Rn. And in particular, now you can squeeze in P, the generalized momentum, it's the gradient, right? So you can squeeze in the fact that X du is equals to L tilde of X dPH of du. Okay, so again, you should think of P. So you should think of P, the generalized gradient. Sorry, not gradient. So generalized momentum as the gradient, and this is the universal point that should be always thought of. So P is the gradient, and then this corresponds to V, which is the velocity of your particle. This is dPH of x, P, right? And P is dUx. Okay, so there's a correspondence between the P and V, and you can use compositions to see that L composed with VTL composed with L tilde is VTH, or vice versa. You have VTL is L tilde composed with VTH composed with L. In other words, you can go, using L and L tilde, you can go between Lagrangian and Hamiltonian framework. And you see that, you want to prove, you want to show that VTH of gamma is a subset of gamma, right? So that's we want to prove. And you can just now recall, the box you have here, the first red box you have. So that can be rewritten as L composed with VTL composed with L tilde of gamma is a subset of gamma. Okay, so that's the equivalent point. And now you can move the curly L, you can take curly L tilde of both of the sides. So that allows you to see that this is equivalent to the fact that phi t L composed with L tilde of gamma is a subset of L tilde of gamma, right? As L tilde is nothing but L inverse. Okay, it's just a simple fact. So now you rewrite this L tilde of phi of gamma, sorry, L tilde of gamma, you just rewrite as gamma tilde, right? So gamma tilde is gonna be what? You can write down explicitly if you feel confused. Again, L tilde, you have the definitions which I just highlighted over there, right? So L tilde of gamma, hold on, am I confusing you guys? Give me 1 second. Oh, okay. Yeah, so there was a question. So is it supposed to be L instead of L tilde? So L is the Lagrangian, right? So L tilde is the map. So I mean, L tilde is we define to be the map mapping from L tilde is a map mapping from XV to XP. So sorry, curly L is the map mapping from XV to XP. So it's not the Lagrangian, and curly L tilde is the curly L inverse. Sorry, I said many curly, so I'm confusing myself as well. but it's a curly L, not the Lagrangian. Um, so yeah, I think that up to this point that's correct. And
Oh, I'm a little confused because in the definition of L tilde up here, we're sending XP to X and DP, but then later we're applying L tilde to X and DP.
yeah, so that's correct. I think you are right. We are sending from, so I'm writing XP. I'm also confused. Give me 1 second. So I'm writing XP equals to, yeah, it should be L. You're right. It should be curly L. I mean, so that, is it your question? So XP is L of XV, right?
Right, right.
Okay, thank you. Yeah, that's why I'm also confusing myself with lots of curly and tilde and thank you.
I see. Thanks.
Yeah, that's correct. So let me correct something on the left panel. So yeah, this is absolutely the point. So I I should have x du is L of x dph of x du. So that okay. Let me put a box here. Oops. So I'm correcting this box here on the left panel. It should be curly L, not curly L tilde. And then I should correct the few lines below here. It should be that L tilde composed with phi TL composed with L equals to phi TH, and vice versa. I should have phi TL is L composed with phi TH composed with L tilde. Yeah, absolutely. I'm sort of switching the tildes in the left and the right, so that's why I was confusing. I was confusing with myself as well. So now I have to correct this one on the right panel as well. So now it makes more sense. So I should prove that L tilde composed with phi TL composed with L is a subset of gamma, right? And then I can compose both of the sides with L. So that allows me to say, to try to prove that, hold on, right. So that's what tells me to prove that I'm still feeling a little bit uncomfortable. No, this is correct. Okay. So what I have to prove here, I'm highlighting it here, is correct. So this is what I have to prove, right? And then I define gamma tilde to be curly L of gamma, and curly L of gamma, if you look back at the definition, I want curly L tilde. doing something wrong? Okay, let me write out gamma tilde and I'll come back to this point, with too many curlies and I got really confused with x in t, and so this is surely correct. So gamma tilde is this one, and I want to, now I need to show, so we need to show that phi TL of gamma tilde is a subset of gamma tilde, right? So this is what it meant to be, that it's invariant under the Lagrangian flow. Okay, now let me come back to this thing. So gamma is x du, right? So it's xp. So somehow I should have this one is curly L, it's not L. So if this one is curly L, then it should be L here. Yeah, so I'm correcting again the right hand, the left panel. I think what you mentioned to me was correct, and I was messing around again. So it should be like that. Okay, now I'm good. So it should be L composite phi TL composite L tilde is phi TH. Okay, okay, good. I'm sorry about that. Okay, so now I see what I need to prove, right? I need to prove this fact that gamma tilde is an invariance under the Lagrangian flow. And this proof I presented to you now is an ad hoc proof. Why is it ad hoc? It's ad hoc because we knew already what we need to prove. So we knew that we need to prove gamma tilde is invariance under the Lagrangian flow. And, so as in the Lagrangian framework, you can see the curve gamma s gamma dot s, right? And if you compare gamma dot s with what is written up here for the gamma tilde, right? Then you can guess that gamma dot s is nothing but dph of gamma s du of gamma s. Okay, so that's why I'm saying that the proof I'm presenting to you now is an ad hoc proof, because we can guess the form of the velocity of the curve. So we guess that's the point, and then we just plug in, right? We plug in and see that, do we have invariance under the Lagrangian flow? Okay, so so it's ad hoc for now. We come back after the proof and explain that this is actually rather natural, but bear with me for now. Okay, so that's exactly the proposition on the left panel. So we assume that gamma is a curve, so that is satisfying this property that gamma dot is equal to dph of gamma du of gamma s for s in IB. Again, hand wavy, right? Because, again, we knew and then we assume. So we assume that that's the case. So if this is the case, and we are able to prove that the difference of u evaluated at the two endpoints is equals to the action functional on gamma, surely plus a normalized constant c times b minus a. Okay. Moreover, from here, I'll recall why, but from here we can imply magically and immediately that gamma is a minimizer of the minimizing problem, right? So, I mean, not only that, gamma satisfying a nice differential equations, from what we guessed, but then automatically, because of the underlying PDE, we can imply that gamma is a minimizer of our, minimizing problem. And once you have that, you're gonna get right away that gamma is in CK, okay? And from here, eventually we deduce that gamma tilde is invariance under the Lagrangian flow, okay? Right, so let's see how everything matches and being combined together. And you know, not surprisingly, we are using exactly the duality inequality again, and we use the fact that when do we have equality? Okay, so proof. Again, once we are done with the proof, then we're gonna do some deep discussion here. Why and how? Again, do stop me if I'm making mistakes about notions and I'm confused again. Okay, so again, so recall that we have gamma dot s equals to dph of gamma s du of gamma s. Okay, um, so clearly we are using the inequality becomes equality in the Lagrangian form, right? Again, we are using it again and again and again, that you have, in general, that you have v is dp, right? So v is dph. Again, this plays a role as v, right? That's when equality happen. So you have v dot with p is du, right? So this is p. So you have v dot with p equals to h of x p plus l of xv, right? Okay, so that's always, when we are trying to use the duality, and again, here we have exactly that equality happens. Okay, so you use that, and then you notice that the h, the Hamiltonian evaluated here, is exactly at the C energy level. So this is C, right? Plus L of gamma S is gamma S. And we chose, again, ad hoc, in an ad hoc manner that we chose that dph of gamma, du of gamma S is nothing but gamma dot of S. Okay, so this is C, and this is gamma dot of S. So naturally we end up with this very nice equality, right? And that allows us to rewrite, the whole equality becomes du of gamma s is p dot with v is gamma dot of s, again by default that we chose it, is equal to c plus l of gamma s, gamma dot of s. Okay, so we have that. And now you just need to integrate, right? Again, this is the same trick again and again and again. The left hand side here is nothing but d over ds of u of gamma s, right? So you have that, and then you just integrate to u. Let's put the red box here to use the one on the left panel here. Okay, so you have nicely that you evaluated at the two endpoints equals to the action on gamma. Okay, now this is easy because earlier we already proved certain results, right? Earlier we have already proved that. I can recall quickly the proof. It's the same game. Earlier we have proved that for any other curve eta with same endpoint. Okay, so maybe let me draw a nice picture here. I have this is gamma of I, gamma of B given, and gamma was the curve that we chose, so that you have gamma dot of S is dph of gamma S du gamma S. So this is by design, gamma having that velocity. And then, if you choose eta to be any other curve, piecewise C1 or something, then we have proved earlier that you would have u eta b minus u eta I is always less than equals to the action function on eta, again with the normalized c times b minus I. Again, the proof of this is simple, right? You just write exactly, okay. You just write exactly, you know, write exactly the duality formula and the inequality again. The left hand side here just equals to integral from I to b du of eta s dot with eta dot of s ds. And this is again less than equals to integral from I to b L of eta dot plus h of eta du of eta ds, and this is c. So you have the same thing, right? So you see that we are using over and over again the fact that we have the duality inequality, but also by using hidden here is that we are using the fact that when you go from the Lagrangian to the Hamiltonian framework and vice versa, you're doing it optimally, right? When you choose V is dph, that means that you allow for the equality to happen, and that's exactly when gamma dot is designed to be like that, so it's optimal. So therefore you have that gamma is a minimizer, right? And then you get gamma is ck, and surely gamma satisfy the Euler Lagrange equations, right? So that's really beautiful, right? This is not easy. It doesn't come for free. Um, we have been wasting a lot of time developing the whole uh, developing the whole theory for it. So it's rather striking. After 10 lectures, now we can conclude nicely. This again hidden some points here I have not explained. Okay, so far so good. We are done with almost everything except the claim that on the left panel here, that gamma tilde is invariant under the Lagrangian flow. Okay, so let's see how does it go. Now you take a point, right? X naught V naught, which is equals to X naught dp h of X naught du X naught is in gamma tilde. So we know that gamma satisfies the Euler Lagrange equation, right? You know that's why it's remarkable, because again we have developed the whole thing and we know that gamma satisfy the Euler Lagrange equation. So what is gamma dot here? If you start the Lagrangian flow, phi t L of X naught V naught, right? So uh, it's exactly gamma dot, and again by design everything was chosen so that this is exactly gamma t dph of gamma t du of gamma t, right? And this is surely in gamma tilde. So if you keep a point there and you let it run under the Lagrangian flow, it's always in gamma tilde. So we have the invariance property, and then we are done, right? Okay. Um, so if you look at this proof, maybe you're not so convinced. I mean, like, well, at least I am also not convinced if I'm just thinking of this as a proof with no intuition, and then why is it going like this? And do some of you see any points that are sort of like hidden here, or some points that I'm sort of like I'm not being careful here? Please you can discuss with me, or if you see any subtleties, then please do let me know here. um, Anything that you feel like a little bit sketchy or a little bit weird? Nope, nothing. So let's go back a little bit to see what's going on. I mean, so far up to the point that we show that gamma is invariance under the Hamiltonian flow is equivalent to gamma tilde is invariance under the Lagrangian flow. That's fine, right? Then we were defining the gamma dot to be like that. So the first question you can ask me right away is that, like, what's the ODE theory for that gamma dot, right? It's a natural question that we can ask ourselves. So you can start with gamma to be, starting with any point, right? So maybe let me start some points of discussions, and then you can tell me. So points of discussions. The first thing first is that what's the ODE theory for the ODE. So gamma dot s is equals to dph of gamma s du of gamma s. Let's say for s in R or s in AB, doesn't matter, and you start with gamma 0 equal to x0, let's say. Okay, what's the ODE theory for this simple looking equation? Can you tell me? Well, I mean, if naively we assume everything is nice, then surely you have an ODE theory for this one, right? But the point here is that you have H is nice, C2 or CK doesn't matter. It's nice in the first lot, doesn't matter. X is compact in the torus, or you can make it in Rn with certain good enough assumption at infinity, you're fine. What is troubling here is that you have this du. Okay, you have du is a continuous function, right? So so we know that du is a continuous function in the torus. And that's fine, but it's not C1 or anything, right? It's only a continuous function. So if you wish, if you want to make it clearer, you can define, let's say, the vector field. Let's see, what's the vector field should I use? F. Okay, f of x to be dph of x dux, right? That's exactly that. Then again, as du is only continuous, so we only have that f is a continuous function in the torus, right? And again, f is continuous in the torus, so everything is compact, it's bounded, it's nice, but we don't have that it is Lipschitz, right? So when we don't have that it's Lipschitz, then what's the ODE theory we are using here? I mean, how can I make sure that my ODE is defined for all S in R, right? Because we are saying that you can run the Lagrangian flow forever. How can I make sure that this ODE is defined for all R? Can some of you tell me what's the point? And do you have uniqueness here? Do you have anything here that I can make sure that the equations is surely nice? And again, later on we're gonna talk about when times goes to infinity, either plus or minus infinity, then how would we face that? Okay. Um, you guys are really quiet today, but nevertheless, here we cannot use the regular ODE theory, right? Because the regular ODE theory would say that we would need F to be Lipschitz, right? But here F is only continuous, so we can only use the piano theorem for ODE, right? Um, so the piano theorems, this only gives existence, but not uniqueness, right? Okay. So the piano theorem says that if your function is continuous, actually it's only need to be locally bounded, then you can define your ODE for a tiny piece of time. So what it's really meant here is that, you know, when you look at this ODE, you have gamma dot equals to f of gamma s, and you have gamma 0 is equal to x naught. Then first of all, you only have existence for a short interval of time, say s is in minus delta to delta. Okay, but then the point is that if again um, if your vector field is only locally bounded, then this delta, you know, can be depending on locations, but in this case, luckily f is uniformly bounded. So, you know, you can keep extending your ODE gamma to, you know, like minus n delta to n delta, and let n goes to infinity to have gamma defined, you know, on the whole on the whole R, right? So that's the first point. This is very subtle, but what it tells us here is that actually uh, uniqueness is not guaranteed at all. I can give you quickly an example, maybe, you know, in the last minute or so. I mean, it's just a classical example in OD. Nevertheless, this is good enough that we have existence, and existence is the key here for us to find that. You see that, okay, you see that the gamma dot here is just going from 0 to any places, any points. It doesn't need to be unique, but, you know, from any points A to B, it corresponds to a minimizer. So you have gamma is ck, and ck is satisfied the Euler-Lagrange equations, and correspondingly is invariance under the Lagrangian flow. That's sort of like really that, you know, what we have, right? And it's not clear at all to us, you know, like um, how should I put it? It's not clear at all to us how, I mean, or you know, in general, for the general minimizing problem, whether we have uniqueness or not, and that's precisely corresponding to this point, right? So I also should say here that a remark is that in general, we also don't have uniqueness of minimizer to the action functional. Okay, in general, there are some cases that are different, but I want to make sure that this is the case, and this corresponds to exactly the point that we just discussed. Okay, and 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 this is also saying that, you know, when we need to use the P&O theorem for ODE, you know, then it also tells us that that's one of the reasons why we can't just use the Hamiltonian framework, because when we use the Hamiltonian framework, we were using a bit more of the regularity, and there, when we use more of the regularity, then we have more of the property, or in this case, you know, if du were C1, you know, if u were C2, then you would have right away that f is Lipschitz, and then you can see that your ODE has a unique solution, right? and that corresponds exactly to the Hamiltonian framework, but here you don't have that. Okay, so the second remark is that, oops, fine, that's one is okay. Second point is that if we have that U is in situ of the torus, then the map, the vector field of x equals to dph of x du of x is Lipschitz, right? Then we do have uniqueness of gamma to the OD. Okay, but if it's only C1, we don't have that. So luckily, I mean, it's a technical point, but luckily when we transfer it to the Lagrangian framework, it works here because we have a good, good existent theory for the OD without requiring the Lipschitz property. It's remarkable, but fine. It's sort of something that I don't know what to say. It's sort of something that in a way, it allows us to bypass the difficulty. Okay. So the third point I want to discuss is that why did we choose gamma dot s equals to dph of gamma s du of gamma s on the first place? Right? Okay, assuming that we don't know that sort of like framework earlier of going from invariance under the Lagrangian flow to invariance under the Hamiltonian flows and vice versa, if we only look into the problem in a naive way, then how do we know, to choose this sort of like smart choice, But if you look back into the proof, right? I mean, if you look back into the proof here that I listed here, you have, always the inequality, always that if you goes under the let's look at the left panel here. If you goes under the Lagrangian flow, then you have to consider the action functional, right? So let's forget about the earlier equivalent relations, but let's just look into this action functional. For the action functional, then surely, as we know that satisfying the Hamiltonian OD is equivalent to being an extremal curve for the Lagrangian flow. So being an extremal curve for the Lagrangian flow allows us to say that, we should have, exactly that the equality happens, right? So maybe let me say it here. So sort of we see that gamma should be an extremal curve in the Lagrangian in the action functional. I mean, that's sort of the point, right? Because if it satisfies the Hamiltonian ODs, then we already proved in the previous 10 lectures or so that it's equivalent to being an extremal curve in the Lagrangian framework. And once you have that, then you can see that what did I say? Then you can see that sorry, you go back to this inequality on the left panel, and you see that you should have equality, right? So when you see that you should have equality, that's exactly tells us that the equality on the left panel happens. If you look at the right panel here, you should have the equality for eta dot, right? Eta dot should be exactly dph, right? And dph is exactly dph of this Hamiltonian. Okay, so that suggests exactly that even if we don't know the earlier equivalence relation, we still can see how does it go, right? So let me repeat it here. So if that is the extremal curves, and we should have equality in, you know, the inequality that you have du of gamma s dot with gamma dot of s ds. Again, this is, you know, still guessing, but it's better. I'm just saying that. I'm not saying that, you know, everything is natural. Okay, so you should have this one becomes equality, and this happen if and only if that you have gamma dot of s is dph of gamma s du of gamma s. Okay, so that's how and why. So, you know, at least once we understand this, it becomes more natural to me. Although again, you know, without the piano, or sometimes people say Cauchy piano theorem, then we would be doomed, right? So that's sort of a very essential point. And note that to develop Wickham theory or some other theory like this, if you develop it in in infinite dimensions, there are various sort of theories that people have been trying to do for, you know, infinite dimensions or something like that, and one has to be careful with this sort of low coexistence theory, you know, whether you can bring it to infinite dimensions or something like that or not. So one has to be careful when trying to develop this theory for general setting. Okay, so as a final point, I'm nearly out of time. So the final point of discussion is that what if U is not C1? Okay. So, you know, for those of you who are, you know, experts in classical mechanics or canonical transformations, or for those of you who come from, you know, astronomy or some other fields that you have seen canonical transformations, that is typically the case that one needs to have the things as smooth enough. You know, so C2 was kind of a bare minimum, right? But then we are already reducing it to C1. And for C1, we face certain difficulty, but we can still do it. Now I'm saying that what if we don't have that U is C1, right? Again, this gonna be, you know, it's gonna take us a long time to get here. But in general, it still makes sense to talk about solutions to the equation h of x du x equal to c, where u is only Lipschitz. Okay, so it still makes sense. I'll give you maybe a quick example why, but then what I'm trying to say here is that if u is only Lipschitz and the whole theory we have developed for this part, you know, is completely broken. You know, if u is only Lipschitz, then you know, then how can one, for example, define the OD for gamma dot s equals to dph of gamma s du of gamma s? You know, in this case, this is not continuous anymore, right? Du can have jump. For example, if you look at the functions like this, right? Then du can jump from -1 to 1, -1 to 1. So your right hand side is essentially only L infinity or something. Then you don't really have a theory to develop local existence for this kind of ODE, and everything is broken. So it's rather dramatic, but it's something that we're gonna need to address later, and you know, we're gonna develop a whole theory for this later. So actually I'm out of time, but let me give you just one example why we cannot expect that U is C1. Okay, some of you surely know this example, but some of you haven't probably seen this one. So you can see that this one is the domain omega with the boundary, assuming that the domain omega is homogeneous, so the light can pass through any point with constant speed, and assuming that the speed of light is 1, okay, by normalization. So you are letting the light sort of passing through the boundary of omega to get inside the domain, okay? And you define u of x to be the time it takes uh, for the light to reach the point x, okay? Then in this case, you see that u of x is exactly the distance functions from x to the boundary of u or omega. And later on, you're gonna see that you solve the so-called Eikonov equation, PDE, that you have du equals to 1 inside omega and u equal to 0 on the boundary. This is an extremely important PDE to, to discuss. So it's just a distance function, right? It takes how long it takes, from the boundary to reach to the point inside. And if you draw the graph of u, for example, if you take omega to be just the unit ball, then the graph of u is just going to be a cone, right? And it has singularity at the origin. And in general, if omega is very complicated, then the distance function has a lot of singularities. And you see that u is not C1. There are certain singularities that happens. So it says that we cannot in general expect that our solution to be C1. Okay, so everything is certainly quite uncertain. But we're gonna take a lot of time to talk about this later. I just want to make sure that we have emphasized 3 points, that if u is C2 or u is C1, then we have invariance, and we use both Hamiltonian or Lagrangian framework. And in general, you shouldn't be C1, and that is a big question mark, but don't worry about it for now. Okay, so I'm done. Are there any questions or concerns? And am I going too slow or too fast or anything? Can you just, okay. Yeah, because you guys are really quiet today, so I really don't know. Is it okay, or is it fast, or is it slow? So, Jen Hui told me it's okay. Okay. Sorry, I couldn't hear you. Can you say it a bit louder?
Yeah.
Okay. So thanks a lot again. Stay safe and healthy. Sorry. Yeah, I couldn't hear you again. Can you repeat your last sentence?
Sorry, I think, yeah. Can I ask a question?
Sure, sure. Yes, go ahead.
So about the existence of
Mm-hmm.
the ODR dot, yeah, gamma, sorry. And then can we just say, because we know the existence of the minimizer, so it solves the ODE?
No, okay. So you see that so the proof goes like this. So first of all, we consider gamma the OD to be like this, right? And assuming that we have such a gamma, then you know that it's a minimizer, right? So you know that it's a minimizer, then it's CK, and then it satisfies the Euler-Lagrange equation. Okay. And now, again, remember that what do we need to prove? We need to prove that gamma tilde is invariance under the Lagrangian flow, right? So what does it mean by invariance under the Lagrangian flow? Is that you take a point x naught, v naught there, right? And then you run the Lagrangian flow. And the Lagrangian flow is, okay, maybe let me mention it down here. So you take, for some reason, okay. So you, one second. So for some reason, my pen is not recognized. Okay, I guess. So you take, okay. No, I couldn't write it. Maybe okay, maybe let me just say it because I couldn't write it down. So so what you take is that you take the Lagrangian flow, right? You start with x naught v naught, and you start the Lagrangian flow, which is gamma gamma dot, right? And gamma gamma dot satisfy the Euler Lagrange equation, right?
Yes.
So, but earlier, if you run uh, so if you satisfy the Euler Lagrange equations, then it's how should I explain it better? So when you um, uh, then the previous curve gamma gives you exactly what you need, right? Because that's exactly phi t of L. Does that make sense? Remember that phi t of L is a curve that is well defined, right? Phi t of L is just satisfying the Euler Lagrange equations, and for Euler Lagrange equation, when you write down, there's no u, right? You know, so so that's a very good question. Unfortunately, my pen is frozen, so I cannot write down. But what I meant here is that the Lagrangian flow is just satisfying the Euler Lagrange equations. You have like dt of d over dt of dv is equals to dxl, right? So that's the Euler Lagrange equations, and then but what we have done here is that the gamma we chose earlier here, the gamma we chose here turns out to be exactly that it satisfies the Euler Lagrange equations, and then it's then exactly the Lagrangian flow.
Okay.
So the Lagrangian flow is unique for sure. The I take it back. I meant that the Euler Lagrange equations for gamma gamma dot is unique. Okay. But earlier when we chose gamma dot is equals to dph of gamma du gamma, then I don't know if gamma is unique or not.
Okay.
Does that make sense?
Yeah, my question was like, because you said we have to use Peano's theorem, a theorem to say the existence of the gamma. So I was thinking, can we say because the minimizer exists, so we automatically have a gamma that solves the ODE?
The minimizer exists, but then okay. So that's a good question, but I don't know what is gamma A and what's gamma B, right? So the minimizer exists provided that I know the two endpoints. Let's say I
Okay.
start with A, but then I don't know what is gamma B. That's the problem, right?
Okay.
So when you know that the two endpoints, then you can say that you have the existence of a minimizer to your action function. That's absolutely correct. What I'm just saying here is that, okay, you can start your ODE at gamma I, that's fine. But then, you can have actually different solutions to an ODE. It can end up with different values of gamma B. And what I'm just saying here that I have to use existence theory to have that it's go from gamma A to gamma B. Gamma B is something. And then once I know the two endpoints, I know that there exists a minimizer and so on and so forth. But
I see.
earlier, I don't know the endpoints gamma B. I may know gamma A, the starting point, but I don't know the endpoint because you can have different different solution to that ODEs, and it ends up with different endpoint. So it's a very delicate point, and that's a very solid question that you are raising. And this is why I meant that this lecture, it looks very simple, but there are a lot of hidden and weird points. Okay.
I see. Thank you so much. Sorry, I'm like my mic was having some trouble in the beginning. I was
Okay.
adjusting that.
Oh, okay. I see. Yeah, because I didn't hear that. Okay. So
Yeah.
thanks a
Thank you
lot.
so much.
I got to run to the next lecture now. So I'll see you later. Okay. Bye for now. Thank you.
Bye. Thank you.